If a function f has derivatives of all orders at x equals c, which is the center, then the series given in across the top of your screen, this n represents the number of derivatives. N will go from 0 to infinity as you add throughout the list. 0 factorial is defined as 1, so this is okay to be defined this way. Your first term will be f of c, wherever the center is located, plus first derivative of the function evaluated at c, all the way till the upper bound of your sum. And because it's infinite, it never ends. This is called the Taylor series for f at c. If c equals 0, then the series is the Maclaurin series for your function. Let's look at an example. Use the function f of x equals sine x to form the Maclaurin series. And because we're specifically told Maclaurin series, we know the center is going to be at 0. So what we want to do is to establish a pattern, because we want to establish an expansion and see if we can figure out the summation notation for it. You start with your original function, sine of x, and then you keep taking derivatives. Sine eventually will turn back into itself. So the derivative of sine is cosine. The derivative of cosine is negative sine. Negative sine, its derivative is negative cosine. And these are all angle x. And then finally, once you take the third derivative, the derivative of negative cosine x is positive sine x. And we loop back to the beginning. Our center is at 0, so we're going to substitute 0 into the original function and all these subsequent derivatives. Sine of 0 is 0, cosine of 0 is 1. So you finish out your pattern, and you've got a set of numbers that we're going to use to build. I'm going to scroll back up just briefly. This is the part we're going to expand using what we've done with our derivatives and substitutions. Excuse me. After we do our expansion, we're going to do our best to write that as an infinite series. Let's go. Okay. So we take f of c, which is f of 0, that's 0, over 0 factorial times x to the 0. Then we move our index up to 1. This will be the first derivative with 0 subbed in. That's 1. 1 factorial x to the first. Second derivative with 0 plugged in equals 0. 2 factorial x squared minus 1. 3 factorial x cubed. And then finally 0 over 4 factorial x to the fourth. If we continued, we'd be back to a positive 1 over 5 factorial x to the fifth. Everywhere you have a 0 on the numerator, that term actually goes away. It becomes 0. What you're left with are the odd powers of x, the odd factorials, and there is a sign change in here. We have to make sure that our first sign is positive. So this series of terms can be written as the sum from 0 to infinity, negative 1 to the n, over, and then the way to write odds is 2n plus 1. If you double a number and add 1, it's always odd. When n is 0, that gives us 1. 2 times 0 plus 1 is 1 factorial, and we've covered the 1 and the 1 factorial. 2 times 0 plus 1, that's 1. Then, if we move our index from 0 to 1, 2 times 1 plus 1, that's 3 factorial. Negative 1 to the first is a negative 1. And 2 times 1 plus 1, that's 3. And then you try it one more time just to be double sure. When we move up to n equals 2, 2 times 2 plus 1 is 5. So we got a 5 factorial. Negative 1 squared, that's a positive 1. 2 times 2 plus 1, that gives us x to the 5th. So we have, in fact, written the Maclaurin series for sine centered at 0, and Maclaurin series, that will go hand in hand. This infinite series is the Maclaurin series for sine. Let's try this again. We're going to switch functions. We're going to look at e to the 2x. And again, we're going to do a Maclaurin series. The only other option would be a Taylor series, and c will just be something other than 0. Okay, so again, start with your original function, and you take as many derivatives as you need to establish a pattern. So we'll have to use chain rule. E to the 2x, its derivative is 2. E to the 2x, this one's derivative is 4. E to the 2x. Derivative 8. E to the 2x, and so on. Because we're forming a Maclaurin series, we're going to substitute 0 into all of those, the original function and subsequent derivatives. E to the 0 is 1, and so it makes for pretty quick math. This time we've got a set of numbers, 1, 2, 4, 8, and 16. Let's see if we can establish a pattern. Starting with the original, we have 1 over 0 factorial x to the 0. Then you move to your first derivative, that's 2. I'm going to scroll up just a bit. Here we go. 2, 1 factorial x to the first, 4, 2 factorial x squared, 8, 3 factorial x cubed, and finally 16, 4 factorial x to the 4th. Now, none of these are going to go to 0, so absolutely every term is going to get counted when we try to write this as an infinite series. The good news is these numerators are, let me scroll up a second, there we go. Our numerators are all powers of 2. 2 to the 0, 2 to the first, 2 squared, 2 cubed, and so on. So I know my numerator is going to be powers of 2. My denominators, those are all in factorial as you build the list. Same thing with the powers of x. They climb one at a time. I'm going to go ahead and marry these two terms together. They're both to the n power. So e to the 2x as a Maclaurin series can be written as the sum from 0 to infinity, 2x to the n over n factorial. This notation is fine. I made a comment down here, either is just fine. This series and that series, they're equal. It's up to you how you want to write it. Use the function natural log of x to form the Taylor series centered at c equals 1. Start with your original function and just keep taking derivatives. Derivative of natural log of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. Keep taking derivatives. In red, I've written them to try to help you out. Makes it a little easier to find the derivative. That would be a positive 2, x to the negative 3, negative 6, x to the negative 4. In black, it's just the fraction form of what you see in the red. Now, since the series is a Taylor series centered at positive 1, we substitute 1 in to this entire column of functions and derivatives. Starting with the original, natural log of 1 is 0, 1 over 1, that's 1, negative 1 over 1 squared. So every function in its derivative sequence here, plug in a 1. Now we need this final column of values. Let me scroll. Now remember, the very top right of your screen, we have 0 for our first function value. I may have to shrink this down, y'all. Hopefully it's not too small when you're watching a video. Okay, so starting with 0, we have 0 over 0 factorial, x minus 1, because the center is at 1, 0, plus 1 over 1 factorial, x minus 1 to the first, minus 1 over 2 factorial, x minus 1 squared, plus 2 over 3 factorial, x minus 1 to the third, minus 6, that's minus 6 over 4 factorial, x minus 1 to the fourth, and finally 24 over 5 factorial, x minus 1 to the fifth. You can simplify these down a little bit. Notice in the blue ink, I've expanded some of those factorials to help us get a cancellation. This very first term goes to 0 because of that numerator of 0. Our second term, we have a positive 1 over 1 factorial, x minus 1 to the first. Then we go negative, positive, negative, positive. Our signs change every time. So we're going to need a negative 1 sign alternator. All of our numerators get canceled down to 1. For example, 3 factorial is 6. 2 over 6 is 1/3. 6 over 4 factorial, 4 factorial is 24, that's 1/4. 5 factorial is 120. 24 divided by 120, that's a fifth, so that reduces to a 5. Basically, it takes the factorial out of it because the rest of the numbers get canceled down. So our fraction out front is a sign alternator over increasing values of n, beginning with 1, x minus 1 to the power of n. So your denominator factorial and your power always match. We just have to remember to alternate the sign, but we have to game it with an n plus 1. Why is that? Because our 0 term doesn't exist. It's zeroed out. So we're actually beginning with 1s. I started my series at 1 instead of 0. 1 plus 1 is 2, making this a positive, and I needed to start with a positive.